Could explain a lot of things going on these days. Scientists, by the way, did try to intercept radio signals from this mystery object, but
astronomers made a remarkable discovery in 2017. An object from beyond our solar system had entered our midst. This visitor, later named Oumuamua, astonished scientists with its unusual characteristics and surprising velocity. In 2019, the arrival of Comet 2I Borisov, a second interstellar body, proved that Oumuamua was not merely an isolated case. Fast forward to 2025, and history repeats itself. A brand new object, designated A11Pi3Z, has now been detected. Unlike the situation with Oumuamua, where detection came 5 days after it sped past Earth, this time astronomers were prepared. On July 1, 2025, A11Pi3Z was spotted and officially catalogued by the Minor Planet Center of the International Astronomical Union. Its appearance on the Near-Earth Object Confirmation page immediately caught the attention of scientists, prompting further observations. This was no ordinary body tracing a lengthy elliptical path around the Sun. As astronomers started plotting its trajectory, it quickly became evident that this object hailed from outside our solar neighborhood. A sharply hyperbolic orbit revealed that A11Pi3Z is not held by the Sun's gravity, a hallmark of interstellar origins. Initial estimates indicate an eccentricity near 6, the most extreme ever measured for a solar system passerby. Such findings confirmed the initial suspicions. This wasn't just any interstellar object, but one following the most pronounced interstellar trajectory ever observed. To be classified as interstellar, an object must move faster than 42 kilometers per second, the escape velocity of the Sun. A11Pi3Z approaches at an impressive 66 kilometers per second relative to the Sun, far exceeding the required speed to break free from the solar system's grasp. However, additional observations were necessary to verify its true orbit. Soon after its detection, astronomers located earlier images of A11Pi3Z in archived Atlas survey data from as far back as June 25. These extra data points allowed for more accurate calculations, reinforcing the evidence. A11Pi3Z is indeed an interstellar traveler. The Minor Planet Center has now officially listed the object as 3I Atlas, marking it as the third verified interstellar visitor ever found within our solar system. According to its calculated path, 3I Atlas will make its closest solar approach on October 27, 2025, coming within roughly 1.4 astronomical units of the Sun. Unfortunately, Earth will be positioned on the opposite side of the Sun during this event. Its nearest approach to our planet will occur on December 17, at a safe distance of 2.4 astronomical units, well beyond any threat, but still close enough for astronomers to observe it using their instruments. Following this encounter, the object will head outward, expected to pass near Jupiter's orbit around March 10, 2026. Early observations captured it shining at a magnitude of approximately 18.8. Based on its observed brightness and assuming a standard reflectivity, its estimated diameter could be around 20 kilometers. This makes it notably larger than both Oumuamua and 2I Borisov. However, this estimate depends on its reflectivity and whether it's actively releasing gas, either of which could affect calculations of its size. The situation becomes even more intriguing if the object exhibits any non-gravitational acceleration, as Oumuamua once did. Such motion could be a result of outgassing, or, as some more speculative ideas suggest, perhaps even artificial propulsion. This possibility has drawn significant attention to the James Webb Space Telescope. Thanks to its advanced infrared sensors, Webb is capable of detecting the object's thermal signature, which could yield valuable information about its temperature, dimensions, and possibly its shape. Another remarkable aspect is the object's orbital tilt, which is close to 175 degrees. a steep inclination that strongly indicates it is not native to our solar system. The orientation of its trajectory even hints that its origin may lie within the stellar disk of the Milky Way, the broad, flat region where most of the galaxy's stars are concentrated. This presents an exciting possibility. By measuring its speed and entry direction with enough precision, astronomers could potentially trace 3I Atlas back to its home system. However, the opportunity to study this rare traveler up close will be brief. As the object draws closer to the Sun, it may grow brighter. But since Earth won't be in an ideal position, our window for close observation is restricted. Still, by combining data from ground-based observatories, space-based telescopes like JWST, and possibly detailed spectroscopic analyses, scientists hope to determine whether this visitor is a comet, an asteroid, or something entirely new. Recent updates hint at possible comet-like activity, though confirmation will require more comprehensive data. Now that the Vera C. Rubin Observatory has commenced operations, its decade-long legacy survey of space and time is expected to vastly increase the number of interstellar objects discovered, transforming what was once extraordinary into a regular part of astronomical research. The observatory has already made headlines with its inaugural image and the identification of several fresh asteroids, some even passing close to Earth. Over 4 centuries ago, Galileo revolutionized astronomy by directing a small telescope towards the heavens. We are now poised at the threshold of another astronomical transformation. The Vera C. Rubin Observatory, engineered to scan the sky every night with sweeping precision, will capture the universe in constant motion. Its telescope will document everything from asteroids dashing across the sky to stars that suddenly brighten or dim, as well as elusive hints about the universe's deepest secrets, including dark matter and dark energy. Named after Vera Cooper Rubin, who reshaped our understanding of galaxies by asking why their stars didn't move as Newtonian physics predicted, the observatory honors her legacy. Rubin's groundbreaking work revealed that stars at the edges of galaxies travel as swiftly as those near the center, something only possible if some invisible substance, now called dark matter, was at play. Her discoveries provided the first compelling observational support for dark matter's existence. Now, the observatory bearing her name is set to continue her quest. The Rubin Observatory has embarked on its ambitious 10-year legacy survey of space and time, LSST. The goal: to repeatedly photograph the southern sky, night after night, for an entire decade. By layering, comparing, and analyzing this immense trove of images, astronomers hope to detect subtle changes, uncover hidden objects, and track moving phenomena in the cosmos. Making this possible is the observatory's centerpiece, a colossal digital camera, the largest ever constructed for astronomy, rivaling the size of a compact automobile. At the heart of the camera lies a 3.2 gigapixel imaging array, constructed from 189 highly sensitive detectors, each one surpassing the size of typical medium-format camera sensors. These detectors are grouped into 21 units called rafts, all housed within a vacuum and cooled to an ultra-cold -148 degrees Fahrenheit. This frigid temperature minimizes electronic noise, enabling the camera to record even the dimmest light coming from the farthest reaches of space. The focal plane is enormous, stretching over 2 feet in diameter. Each image the camera takes covers a swath of sky 3.5 degrees across, enough to fit 7 full moons side by side. An exposure takes just 15 seconds, and the data is transferred in only 2 seconds. So, what are the Rubin Observatory and the LSST designed to find? The survey is built around 4 primary scientific objectives. The first is to investigate dark matter and dark energy. By charting billions of galaxies and tracking their positions and movements, Rubin will help map how galaxies clump together and move through the cosmos. This mapping will allow scientists to measure the universe's expansion rate and determine if it's changing over time, providing essential insight into dark energy, the mysterious phenomenon driving the acceleration of cosmic expansion. The second goal is to observe the ever-changing sky. Rubin's fast, repeated scans mean it can spot dramatic events like supernova explosions, bursts of gamma rays, fluctuating quasars, or even the first optical signs of a black hole emerging. Within about 60 seconds of each exposure, the observatory's alert system compares new images to previous ones and highlights anything unusual, a process that makes it one of the quickest astronomical alert systems ever created. Third, the observatory will play a crucial role in planetary defense by monitoring objects that pass close to Earth. Its expansive field of view and rapid imaging cadence will allow it to find and track thousands of asteroids every night. And finally, Rubin will help catalog our solar system. By surveying regions beyond Neptune, including the Kuiper Belt and possibly farther, it will discover and characterize distant icy worlds, deepening our understanding of how the solar system took shape and whether unknown objects still lurk in its outermost regions. The Rubin Observatory's first images have already begun to fulfill its ambitious mission. Among the initial releases is a composite view of the Trifid and Lagoon nebulae, two vast stellar nurseries located thousands of light-years from us. This image was assembled from over 678 individual exposures taken during just 7 hours of observing, revealing intricate details in these star-forming regions. Another early highlight focuses on the Virgo cluster, where more than 2,000 galaxies appear in a single frame. Compiled from more than 1,100 separate images, this sequence starts with a detailed look at a single spiral galaxy and then pulls back to reveal a tapestry of roughly 10 million galaxies. It also spotlights 46 variable stars, each one subtly pulsating. These glimpses are just the beginning of the dynamic celestial landscape Rubin is set to unveil. Over the coming decade, the observatory is predicted to discover up to 100,000 variable stars, some as far as 1 million light-years away. Even in its first 10 hours of operation, Rubin identified 2,104 brand-new asteroids within our solar system, including 7 that come close to Earth. While none of these pose a threat, the real achievement lies in Rubin's remarkable speed and efficiency. To put it in perspective, all other observatories around the globe, both on the ground and in space, typically find about 20,000 asteroids per year combined. In contrast, Rubin is expected to reveal millions of previously unknown asteroids in just its first 2 years of the legacy survey of space and time. That's astonishing. Night after night, the observatory will sweep the sky for anything that moves, brightens, or dims, including objects that defy our expectations, much like Oumuamua, the first identified interstellar visitor to pass through our solar system. Should another such object enter its view, Rubin will detect it and provide immediate alerts. But the observatory's impact doesn't end there. Over time, it will produce trillions of data points, tracking billions of stars, galaxies, and asteroids. This immense trove of information will be so comprehensive that it's sure to inspire new questions, some of which we haven't even imagined yet.